So welcome everyone to my lightning talk, which is on ILGPU. My name is Tor Haugen. I work for Novanet, same as Per, a consulting group based here in Oslo. My intention is to demonstrate that the power of your GPU is perhaps much more available to you as a .NET developer than you might think. Now, using the GPU for general computing has been pretty mainstream for a while. And there are several platforms available to do this. The two best known ones being OpenCL by the Kronos group and the CUDA platform by Nvidia. Now, you can go in to the web pages and check the documentation for these platforms. And it's pretty technical. For us .NET developers in particular, it can appear somewhat inaccessible. You'll have to deal with multiple language projects, special compilers, etc. You need to use C++, perhaps. It's all a bit daunting. Personally, I was despairing if I would ever get around to trying it. Then I discovered ILGPU. It changes all that. The ILGPU platform contains a just-in-time compiler for taking your kernel code, the code you want to execute in parallel on the accelerator, and transpiling it to the underlying GPU format straight from the compiled .NET IL in your assembly. I'll show you how that works. With ILGPU, you can just install a NUGET package in your .NET project and start working. Yes, it really is that simple. I'll make a kind of a Hello World project, a Hello World for GPUs. I'll be rendering the Mandelbrot set. It's just as useless as Hello World, but it's much prettier, and it benefits wonderfully from parallelization, as you might see. The Mandelbrot set, I won't get very deeply into this, but it's we need a quick primer just so you know what we'll be doing here. So it's a set of complex numbers, first investigated in the 1980s. It's characterized by an infinite amount of complexity emerging from a simple iterative function. Around 1985, people realized that this complexity can be visualized using computers. It was a huge hit. Because it yields some amazing imagery. And it's been the iconic example of fractal chaos ever since. So here's some math for you. We don't need to know a lot about complex numbers for this demo, only that they have two parts, A and B, called the real and imaginary parts. So a complex number C is actually a sum of a real part, A, and an imaginary part, B, times I, where I is the square root of -1. They have well-defined operators like addition and multiplication, and they follow simply from the definition. So the actual set, for some complex number C, we define a series of complex numbers Z0, Z1, Z2, etc., such that each value of Z equals the previous value squared plus C. That's this here. Now, as you repeat this procedure, this iterative function, the values of Z that are produced will either remain small or eventually diverge. They will run off to infinity. If they remain small, however many times you iterate, then C is a member of the Mandelbrot set. Sounds simple? But in fact, even arbitrarily close values of C can behave very differently. And this yields an endless complex variety, as we shall see. So to visualize it, since complex numbers have two parts, A and B, this means that they fit on a plane, a coordinate system, with the real part along the horizontal axis and the imaginary part along the vertical axis. This is called a complex plane. So what we do is this. We run the iterations for each C, for each pixel. If the series doesn't diverge, we color the pixel black. That's by convention. Of course, it could be any color, but that signifies it's part of the set. That's the interior of the figure there. Otherwise, we give it another color depending on how quickly Z diverges. So, here's some code. The iterate function here takes a complex number C and the maximum number of iterations to perform. Now, we happen to know that if the modulus of Z exceeds 2 at any point, the series is going to diverge. So that's our exit condition. The function will return a value between 0 and limit. A return value of limit means that C is a member of the set. Now, we'll do some code. I've made a simple WPF application. I'll show you first the CPU version of this iterator, and then I'll show you the ILGPU alternative and what it does for the render time. So, there we are. Good. So, this first here is application code. This is mostly WPF code, and we don't need to worry about it. But you can see here that there's a call to an iterator.iterate range. Now, all these parameters that we send in start with height, step, and a palette. That's application code. You can control it with the mouse and key and so on. You'll see it afterwards. But the point is that having called the iterate range here, the result of all these iterations will be in a 2-dimensional array. And now, the actual, we'll have to look at this complex struct that I made first. It has 2 parts, A and B. And it defines these operators, plus and multiply. So there's some mess there. It also defines the modulus, which is basically the distance from the origin to the point in the complex plane. It's kind of the absolute value of the complex number. Now for the actual iterator. This is the CPU iterator. And you recognize the function? It takes a complex number, a complex double. It initializes Z to be 0, and then it runs the loop. And the point is, we do this loop for every pixel in the image. So this is compute intensive. So for every loop, we square Z and add C, and then we assign it back to Z. And then finally, we check the modulus. That's the modulus squared. That saves us a square root operation. And if it's greater than or equal to 4, then we're done. It's not a member of the set. And finally, we return this value. And so the value returned will depend on whether it's in the set or not, or how quickly it diverges. So to do this for all the pixels in the image, we have this iterate range method. It takes a starting point, a width and a height in pixels of the image, a step, which is basically a scaling factor, the maximum number of iterations per pixel, and a 2-dimensional array for the output. And then we simply parallel 4 over y and x. Each y and x yields a complex number c, the corresponding complex number for that pixel. And then we pass it to the iterate function, and we assign the result to the output. And that's all. The result looks like this. That's on the wrong screen. I'll put it up there. And this is the Mandelbrot set. This is all based on that simple iterative function. But you can see it's really slow. The rendering time here is about half a second. So when I zoom in, it's somewhat sluggish. It's pretty, but it's slow. So we'll do it in ILGPU instead. So this is my GPU iterator. If we start by compressing everything, you can see that it has the same thing. It has an iterate function, but it also has some fields, and it's disposable because some of those fields hold unmanaged resources. So what we basically do here, we've imported the namespaces from ILGPU. We establish a context, an ILGPU context, and we create an accelerator. There's lots of very different ways to do this. You can enumerate your devices and everything, but the defaults work right out of the box. Now, the iterate function here is a little bit different because we need this is the function that will be run on your graphics card. This is the kernel. And this kernel needs to do all the work itself. So it's impossible to pass it the actual complex numbers and stuff. So instead, we pass it the x and the y for the pixel. Where are we? We send it the start and the step and the limit that we had. And it also passes the output buffer to put the result in. So it's essentially the same, only we calculate C inside here. And then we do exactly the same iteration. We initialize sets, we iterate through them, we do the set equals set squared plus C, and so on. And then finally, we put the number of iterations into the output. So, how to do this actually on the graphics card? This is the trick. In the constructor, we create a so-called launcher delegate. We call a method on the accelerator called load autogrouped stream. This is the simplest, most default way to do this. There's lots of other ways. You can control this if you really know what you're doing. But the point is, you can see that it has type parameters that match the signature of the iterate function. You can see they are the same. And we pass it a reference to the iterate function. And what this method does is it goes and fetches the IL for your kernel. It transpiles it into whatever underlying code the graphics card wants, sends it to the graphics card, and then returns a delegate which you use to actually run it. And so for the iterate range method that I had, this is the same method that we had on the CPU iterator. This is the one that's called from my application code. I just switch the iterator that I use. So what we do here, it's just a little bit different. First, we allocate a buffer on the graphics card. We call a method on the accelerator instance. It's called allocate, the width and height. This is a two-dimensional buffer. And then we call the launch delegate. And the first argument to the launch delegate is this index 2 of width and height. What we're doing here is we tell ILGPU and the underlying CUDA or whatever it is, OpenCL perhaps, we tell it, please call my kernel function with all values between 0 and width and 0 and height. And then we pass it the fixed arguments, the start and the step and the limit, and the view to this buffer that we just allocated on the graphics card, so that the kernel can write to the buffer. After we've done that, we call accelerator synchronize to wait for it to finish. And that's, ladies and gentlemen, that's all you need to do. Finally, when this is finished, the results are in the buffer. We copy the buffer to the output array, this one, and then we dispose the buffer. So, what does that look like? Obviously, hang on. Obviously, it looks the same. But now I'll check this little box I have here to use the GPU accelerator. And you see that the speed is now something else. So all these, there are perhaps a few million pixels in each of these pictures. And at this point, I'm doing 100 iterations for each of them. So it's like 100 million iterations for each frame. We can also we can change the number of iterations, which will change the fidelity of the picture. So if we go in here, we can tune it. And basically, you can watch this for hours. This is just fun. I can also change the palette that we map it onto. Binary is boring. Grayscale is somewhat less boring, but it's always better with colors. So that's what I had for you. Go home and do it yourself. It's great fun.